Throughout history, there's been one form of structure synonymous with great public events. It's the dome. Domes have an almost mystical ability to create a sense of awe in the humble visitor. And to engineers, meeting the demand for ever larger domes has been an enduring challenge. I'm in London at the site of the Millennium Dome, and in this programme, we'll explore the mystery and the glory of this and two other great domes. But we'll begin in Florence. No other city in Europe, with the exception of Venice, trades off the past in the way that Florence does. In addition to its fantastic array of buildings, the list of geniuses who lived and worked here reads like a who's who of art and literature. Dante, Michelangelo, Botticelli and Giotto, to name but a few. But to any visitor like me, picking their way through the Florentine streets, there is one incredible building tantalizing you on every turn. It's dominated the skyline of the city for over 500 years, the spectacular Duomo by Brunelleschi. In a design which brought together science and art to create a new standard for the future, the dome of the Cathedral of Santa Maria del Fiore marked the arrival of the Italian Renaissance. In completing the building, the city of Florence announced to the world that it could equal and even outdo the greatest achievements of the Roman Empire. The cathedral itself, begun in 1296, took 50 years to complete, and that didn't include the highlight, the soaring octagonal dome. At that time, domes were built by supporting the underside with timber scaffolding. But in Florence, the span was so great that no formwork could bridge it completely, so the cathedral had to go domeless even after completion in 1357. Quite simply, they'd started a project with no idea of how to finish it, and it was to be another 60 years before a competition was launched in 1418 to find a viable design for the dome. The winner was Filippo Brunelleschi. Armed with a 12-foot diameter model and a series of impressive innovations, he eventually won the contract that would take a further 16 years to complete. Brunelleschi's major achievement was to complete the dome without any timber supporting structure. He argued that a dome built up in stages, in rings, would be entirely self-supporting. This technique had never been used on this scale before. Although there was no timber structure supporting the roof, Brunelleschi built a working platform for the masons, cantilevered out on great wooden beams socketed into the side of the cathedral here. There are 48 of them right round the wall. The holes are huge. Imagine what the beams were like fitted in there. One major innovation was a double skin. The dome has an inner and an outer shell. But at over 4 meters thick, it is also extraordinarily heavy, weighing 25,000 tons. You see, domes carry their weight downwards and outwards, and they need to be buttressed or supported around their perimeter to stop them cracking vertically. Historically, great domes had been buttressed around their sides, and here in Florence there are 3 small domed apses which provide some support. Brunelleschi realized that this support was not enough. He used a system of stone chains with iron links like this around the perimeter of the dome, tying the whole structure together. But all these systems were not sufficient to stop some movement from taking place, and you can see cracking up the middle of several faces. People often think of cracking as evidence of imminent collapse. It may not look perfect, but masonry can really take quite large movements before it actually falls down. It's incredible. Vasari's frescoes really use the octagonal shape. Hell portrayed at the bottom, moving up through heaven, and topped by that fantastic false lantern. Access to the interior of the dome is by a sequence of staircases up through the stonework. I've climbed right up inside Brunelleschi's dome, between the inner skin and the outer skin. The bricks have a very distinctive herringbone pattern, like the Romans used. Let's go on round the dome, through one of the great internal ribs between the inner and the outer shell that helps to stiffen it, and the dome stretching away above us. Fabulous. Look, and here's a window. You can see right down inside. The inner skin is really thick here, over 2 meters thick. You can see how clearly the masons have laid the bricks downwards in a line that lines up exactly with the bottom of the dome over there. It's just fantastic to be inside here and see this structure. I'm right inside the lantern at the very top of the dome. The lantern lets light down into the cathedral down there. Domes may look a bit like arches, but it's here we can see the fundamental difference. An arch always has a keystone right here in this space to stop the 2 sides falling in. A dome can have a hole because the forces are spread throughout the shell. However, Brunelleschi's octagonal dome was an extra challenge. Smooth, rounded domes can carry their weight more efficiently and can be much thinner. But in the end, it's the great thickness of this dome that makes it work. Looking at the structure now, its 45-meter span could be considered modest in today's terms. However, for the best part of 400 years, the Cathedral of Santa Maria del Fiore had the largest dome in the world. An amazing and unique achievement, the dome still dominates the city skyline in a manner unequaled anywhere else and is recognized worldwide as the greatest masonry dome in existence. The method of construction used here set a pattern which continued right up to the building of the great cathedrals of St. Peter's and St. Paul's. It's only recently, with the advent of new materials, that domes and their design have undergone some radical and spectacular changes. This is La Défense in Paris, a city as famous for its more recent innovative architecture as for its traditional buildings. Steel and concrete, glass and fabric are the materials of this modern development. But there's one building in particular I've come here to see, a classic of design dating from the 1950s, which shows just how modern materials can reshape the traditional dome. This is the Centre des Nouvelles Industries et Technologies, known locally as the Knit Building. It was conceived as an exhibition space for French industry, built to show off France's engineering and scientific prowess in the booming 50s. More recently, it's become a retail development, housing shops and hotels. What we're interested in is the futuristic design of the roof. While it's not a traditional dome like the Duomo in Florence, its rounded shape means it still works as a dome. It's also much thinner. In proportion to its span, it's as thin as an eggshell. The steel and glass walls don't take any of the weight of the roof. They were part of the redevelopment of the building in 1988 and are there simply for aesthetic reasons. and of course to keep out the wind and rain. It's quite breathtaking to see it for the first time, like the vault of some giant Gothic cathedral. In essence, it's triangular in shape, with the weight of the roof channeled down to abutments buried in the ground at each corner. The sides soar up and over the top, giving it a clear span on each side of 218 meters and a height of 50 meters. And there's only one way to get to the top. I'm right at the top of the roof, and what strikes you immediately is the huge, magnificent Grande Arche de la Défense right beside us. And here the great curved roof of the Knit building stretches away beneath us like a cloud, a great snowscape. This is the wall between the two panels, the crown wall, which carries the huge compressive force as they lean together. Let's go on. In great buildings like this, there is always a strong relationship between the architecture and the engineering. The concept of this roof was easy to draw, but much more difficult to build. In the end, it was a French engineer, Nicolas Esquelin, who came up with the solution that we see today. It was built in sections. First, the 6 curved panels, which meet here in the middle, and then the next 3 on either side, and finally the last 3 right out to the edge, way over there. Let's have a look inside. Inside the roof, you can see that it's made up of 2 shells, just like the Duomo in Florence, but they're much, much thinner. They're made of reinforced concrete, and down at the bottom, they're 600 millimeters thick. But up here, they're just 60 millimeters thick. That's this much. The ribs between the top and bottom shells run all the way down to the corners. With the cross walls, they form a honeycomb, very stiff and yet lightweight. Of course, it's not built up using bricks like the Duomo. Instead, they poured concrete onto curved wooden shutters supported on scaffolding underneath. It must have been a colossal undertaking. To keep their shape, all domes require secure foundations, and the Knit dome is no exception. The weight of the roof is channeled down the 3 sides to the ground. As the dome tries to sag, it pushes outwards at the corners, and the force outwards at each corner is equal to the weight of the Eiffel Tower. Inside, the shape of the vaults reminds me of 3 colossal fans meeting at the top. It's quite spectacular. The curved shape of the panels is also very distinctive, and it's there for a good reason. You see, the thin panels in the roof have to carry a lot of force along their length, all the way down to the ground. The problem is that a flat panel would buckle easily, like this. But if you make the panel curved, like that, then it's much stronger. And that's the principle they used here. Neat, isn't it? It's a bold design, even today. And like the Duomo, persuading people that it would stand up was a triumph, even in the 1950s. While the Knip building doesn't look like a dome, the main reason that it stands up is because it is a dome structurally. The forces are spread down through the roof. So domes don't have to be round, and they can be very thin. In fact, as domes get larger, they have to get thinner to be economical. But if you want to make them really large and really thin, they have to work completely differently. The Millennium Dome at Greenwich in London is the largest dome in the world, but it's quite unlike the more conventional dome structures we've seen. It's very thin and it seems to hang in space, held in a cat's cradle of steel wires. But is it really a dome? Well, it's clearly dome-shaped, but the forces at work in this structure are the opposite to the domes in Paris and Florence. Instead of forces pushing from the top down, this dome is being pulled into shape from the base. The shell of this dome is in tension. Unlike our previous domes, whose shells were self-supporting, the Millennium Dome is held in shape by its masts and cables. Basically, it's like a tent. Construction began on the 23rd of June 1997. It was a mammoth job to organize the people and equipment required to build the dome on schedule. The concept of the dome came about only recently. In 1996, a series of exhibition structures were being developed to celebrate the millennium, but it seemed inefficient to make each of them weatherproof, particularly if they were only going to be temporary. Covering the whole show under a single umbrella would create a focus and simplify the design of the individual exhibition stands inside. So the idea for the Millennium Dome was born. A year on, and construction of the main structure is nearly complete. It's an incredible achievement to have got this far, this fast. It's a huge building site at the moment, and it's a fantastic time to see it, because when the exhibition is in place, it'll be very hard to see the structure. The dome will be twice as big as the Georgia Dome in Atlanta, 320 meters in diameter, and the perimeter is 1 kilometer long. The most dramatic feature of the whole structure for me are the cables, which form a giant net in the sky. Around the opening at the top is a tension steel cable ring. All the cables pull outwards on this, and it's vital to the stability of the whole dome. It was particularly important to make sure that any damage up there did not result in the whole tent unzipping. They managed this by using 12 intertwined cables so that even if one broke, the others would be able to share the load. These are the stringers which radiate out from the center. Other cables hold them firmly in position at intervals of 25 or 30 meters. To keep the stringers taut, they're stretched to 2/3 of their peak tension, a load of 40 tons in each cable. This means that they're virtually straight between their supports, which in turn makes it easier to hang the fabric panels. When any material is stretched like this so tight, there is a risk that a panel rips and then it might overload the next panel and so on. So to protect against this, and to stiffen the structure around the perimeter, these stringers are linked by cables, which run right around the dome in a circle. But, and this is a neat trick, they couldn't lie in the fabric, so they are held up above the panels using these rigid wishbones and crisscross cables. Each of the masts is 100 meters high, and they do all the work to hold the dome up. The weight of the dome isn't great, but the masts must collect and channel all the tension forces down to the ground. Each mast carries a compressive force of 1,000 tons, spread down through these 4 struts at the bottom and carried into the ground through the concrete foundations. These backstays hold the mast in position and tension it down to anchors under this concrete block, screwed into the ground like giant tent pegs. The mast is trying to pull up on the anchors back towards the dome, and this concrete slab helps to hold the anchor in position, pushing out from a giant concrete ring beam all around the perimeter. The fabric which has been chosen for the dome had to be translucent, strong, and long-lasting. It's a glass fiber material, coated in Teflon and only 1 millimeter thick. Compare that to the 4-meter thick shell of the Duomo in Florence. There were other cheaper choices, such as a PVC-coated polyester, but it wouldn't have been so long-lasting and it would have absorbed dirt. This should remain cleaner for longer. The Millennium Dome is a landmark in the history of engineering achievement. It's a structure which could not have been built even 20 years ago. It reflects huge advances in computer techniques and material development, which are all part of the excitement of building. But in the end, this dome is all about celebration. For good or ill, it reflects our time in that it is adaptable, temporary, and built to mark a specific moment in history. So the Millennium Dome is very much of its time, both in its engineering and in its function. As we've seen, domes are all about communal space, bringing people together. Their very shape inspires a sense of wonder, grandeur, and security. And that's why, for thousands of years, we've continued to build them, ever bigger. In the next program, it's off to Italy for a rare trip up the world-famous Leaning Tower of Pisa, then across the Mediterranean to Spain to marvel at the twin wonders of the Torres Puerta de Europa in Madrid, and ask what keeps the Torre de Collserola in Barcelona still standing.